Good evening, everybody. It's my pleasure to welcome you here tonight to the Perimeter Institute public lecture. And I would also like to take a moment and express our thanks to everybody who tunes in electronically from around the world these days. We are, of course, coming to all of you from Waterloo, Ontario, Canada. My name is John Matlock. I'm the Director of Communications. Howard Burton, our Executive Director, is away this evening, so it's my pleasure to introduce tonight's speaker. And he is Dr. Daniel Gottesman, faculty member at Perimeter Institute and an adjunct professor at the University of Waterloo. Now, prior to joining Perimeter in September of 2002, Daniel was a student of John Preskill at Caltech. He then held postdoctoral positions at Los Alamos National Lab, Microsoft Research, and the University of California, Berkeley, as a long-term CMI prize winner for the Clay Mathematics Institute. Among his many honors, Dr. Gottesman was included in the 2003 list of MIT Technology Review's World's Top Young Innovators, and named as a Canadian Institute for Advanced Research Scholar in the Quantum Information Processing Program. This evening, he will be discussing quantum cryptography, a tale of secrets hidden and revealed through the laws of quantum physics. Ladies and gentlemen, please welcome Dr. Daniel Gottesman.
Thanks, John, and thanks everyone for coming. So what I thought I would do today is kind of tell an extended anecdote about something that happened to me in the summer of 2001. And since the events had something to do with cryptography, along the way I'll stop and explain what's going on and hope that in the process you learn something about cryptography in general and in particular about quantum cryptography. So anyway, so as I said, this happened to me in summer of 2001. And I was at a conference in Washington, D.C. The conference ended, and so I was on the subway pretty late at night to go home. And two big men walked up to me wearing dark suits, dark glasses in the subway at night. And one of them spoke to me. He said, "Dr. Gottesman?" "Yes." "Please come with us." So I mentioned these were rather large men, and there was not really anyone else around, so I figured I'd better go with them. They took me, we left the subway, got in a car, drove somewhere. It was kind of shaded windows, so I couldn't really see where we were going. Drove for a while. Eventually we stopped, got out. They brought me into a building. So went through the building, kind of labyrinthine corridors, and eventually brought me to a room, and not very interesting room. There was a chair there and a poster on the wall. So here's what it said. Seems like gibberish. But you know, it's maybe there's some method to that gibberish. You see, it's just kind of random-looking letters, but it's arranged in blocks of 5 characters. And this is something that happens with codes. I don't know if you were watching the slides before the start of the talk, but there was a code there that had letters substituted for other letters. So that's called a cipher, and this is going to be another example of a cipher. But in that case, the words were blocked in the same size as the original words, right? So if you had a 5-letter word, you'd have 5 letters. If you had a 3-letter word, you'd have only 3 letters. And that gives a lot of information that helps people to break it. So real cryptographers, they don't do that. They obscure that information by taking the whole thing, cramming the words together, and then breaking it up into blocks of a certain size, in this case 5, in order to hide the lengths of words. You want to hide the information about the message, because it's supposed to be a secret message. So anyway, so these men left me in this room for a while. Luckily, I had a pencil and some paper with me, so I decided I would work to try to figure out what this secret message said. And so after working on it for a while, I found that if you looked at every 3rd character, a pattern started to arise. So if you looked at the 1st letter and the 4th letter and the 7th letter and so on, and then counted the frequency of different letters, there was some definite pattern there. Because, well, in English, the letter E is much more common than the letter Q. Well, unless, like me, you work in quantum computing, in which case Q shows up all the time. But anyway, so take every 3rd letter in this code. And actually, it went on much, much longer than this. So I had lots and lots of letters to work with. This is just the beginning part. So if you take every third letter and look at the frequency of different letters in the system, you'll find that some are much more common than the other. And so fiddling around with that, you figure that the most common letters here correspond to the most common letters in English. And do the same thing for the second, fifth, eighth, et cetera, and the third, sixth, ninth. And what I found was, I know you can't read the small numbers, but what I found is that if you shift the first letter by 14 forwards in the alphabet, and the second by 19 forwards, wrapping around, obviously, Z, A, B, C, D, E, and the third letter by 1, and then repeat that. So the fourth letter also you shift 14, the fifth letter by 19, the sixth letter by 1, and so on. So the key to unlocking this message is those three numbers, 14, 19, and 1, up here in the right-hand corner. And they tell you, given this incomprehensible gibberish, how to convert it into something that makes much more sense, or at least is readable. Here's what it said. As Gregor Samsa woke one morning from uneasy dreams, he found himself transformed in his bed into a gigantic insect. This is a quote, for those who don't recognize it, from Franz Kafka's Metamorphosis. Luckily for me, it had been translated into English, because the original is in German, and I don't speak German, so I wouldn't have had much chance of breaking it if it had been in the original German. I don't know why they had this on their wall. But anyway, so I determined that this is what it said, and then I was kind of out of things to do, because as I said, there wasn't a whole lot else in this room. But maybe at this point it's worth stopping and saying a little bit more about how cryptography works. So this code that I've just shown you is an example of private key cryptography. So suppose you have two people, Alice and Bob, and Alice wants to send a message to Bob. So Alice here on the left, Bob is there on the right. And Alice and Bob previously have shared some kind of secret information called the secret key, or in this case, a private key. And only they know what this private key is. So in the case of the code on the previous slide, that was the three numbers, remember, 14, 19, 1. And they've agreed, in that particular case, that they'll shift the first letter by 14, the second letter by 19, and the third letter by 1. And then they'll do that again. So Alice shifts one direction, and then Bob, when he wants to decode it, shifts backwards. Okay? And so Alice is doing what's called encryption. She uses the key and goes through some procedure that will make the message seem relatively incomprehensible. And then there's an eavesdropper, Eve, down here in the middle. And Eve is listening in on the channel. She wants to figure out what the secret message is. Okay? But Eve doesn't know what this key is. So while she can copy it down, she can write all those strange letters from the last slide, she doesn't have an easy way of figuring out what the secret message actually says, right? Which is, of course, the important thing. Now, in the particular case that I showed you, it was not very secure. After all, I was able to break it with pencil and paper. But there are much more secure messages, which I'll get to, much more secure codes, which I'll get to in a minute. So anyway, so Eve doesn't know what the key is, so she can't read it. But Bob, over on the right, he can, because he receives the message from Alice, and he knows what the key is. He knows that Alice has shifted the letters in a certain way, so he'll shift the letters the other way, and he'll get back the original message. OK, so like I said, the code from the last slide is not very secure. But you can imagine that if you made that key longer and longer, so instead of 3 numbers, it was 10 numbers, or 20 numbers, or 100 numbers, it would become much, much harder to break it. Right? And there's 2 reasons for that. So one of them is I had to look at the frequencies of the different letters. And so to do that, I was only looking at 1 out of every 3 letters. And if the key is 10 numbers long, I'm only looking at 1 out of every 10 letters. So I don't have very many to work with and to try to figure out what those frequencies are. And the other reason, of course, is that when it's 10 numbers long, there's that much more to figure out. And as the key gets longer and longer and longer, it gets harder and harder to break this message, until you reach the point where the key is as long as the original message that Alice is sending. Okay? And when that happens, it turns out there's actually no way to break it at all. Every letter becomes equally likely, and there's no frequency you can look at all. So this is called the one-time pad. So of course, today, we have computers to do all this stuff. We don't do it by hand. So the computer likes to put things into zeros and ones, bits. So for instance, you convert the message into a long string of bits, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, et cetera. Okay, much, much longer than that. And then the key, the private key in this case, is again a sequence of zeros and ones. 0, 0, 1, 0, 1, 1, 1, et cetera. Okay? And then to encrypt, well, you kind of add these, which means that if if the key is 0, you leave the message alone and put the ciphertext, the encrypted message, to also be 0. Oh, sorry, to be the same as the message. Whereas if the key is 1, you flip the bit and use the opposite. So you see, that's what I've done here. So 0, 0, 0, 0 becomes, because we have a key bit that's 1 here, becomes 0, 0, 1, 0. And then 1, that gets flipped to 0, and so on. Okay? And you can easily see that's a reversible operation. So Alice does this to encrypt, and then Bob does the reverse thing to unencrypt. So given the message and the key, it's very easy to create the ciphertext. Given the ciphertext and the key, it's very easy to create the message. But if you only have the ciphertext, you know nothing at all about the message. Okay? And so therefore, it's completely secure. But you can see that there's some significant drawback to this, because in order to do this, Alice and Bob have to share this very long secret key. It has to be as long as the whole message. And you can't reuse it. Because if you reuse it, then you're starting to create patterns again that Eve can take advantage of to try to break the message. In fact, there have been examples in history where people have accidentally used the same key twice in a one-time pad, and messages were broken as a consequence. So you have these long keys. You can only use them once, and then you have to throw them away. And you have to be very careful about how you throw them away. You have to really destroy them so that no one can root through your trash and figure out what the key is. So today, people really do use one-time pads when they want very secure messages. And the way they establish these keys is they send couriers with, briefcases handcuffed to their arm from well, Alice to Bob, in order to send over the key. And of course, what's inside these briefcases is not just random numbers. But random numbers, when you're a cryptographer, are incredibly valuable. OK, so anyway, back to the anecdote. So I was in this room and waiting, and eventually a woman came in. She said, "My name is Alice." Interesting coincidence. I'm afraid, she said, that I can't tell you what we need you for right at the moment. We'll have to wait a little bit longer. But I just wanted to let you know we hadn't forgotten about you and see if you needed anything. I said, well, I was kind of upset at this point, obviously, having waited all this time. If you can't explain what's going on, can you at least get me a computer so I can check my email? This was before I'd moved to Perimeter. I didn't have a BlackBerry then. So I can check my email. She said, yes, I'm sure we can arrange that. So she went out. A couple men came in a little while later, brought in a computer, hooked it up. For some reason, they took down the poster and put up a different poster. I'm not quite sure why. But that was not my interest at the moment, because I was eager to get on the computer, check my email. But then when I tried to send the message, the computer crashed. OK, so I rebooted it, tried again. Same thing. When I tried to send the message, the computer crashed. OK, so I was kind of out of things to do. And again, I was waiting there. So I figured I'd turn my attention back to the poster again. So this one also seemed, at first glance, to contain nonsense. But instead of a long sequence of letters, as the previous poster had, this one had some very big numbers on it. So thinking about this, I thought that since the previous poster had been a code, maybe this poster was a code too. And the number is written in hexadecimal, base 16, suggested to me that maybe it's an example of RSA. So RSA is what's called public key crypto system. So in a public key crypto system, well, so remember in the previous type of code, like the one-time pad, Alice and Bob shared a private key. And that private key had to be kept away from Eve. If Eve learned the private key, then she could decrypt the message just like Bob. But in public key cryptography, that's not quite the case. Now there's two keys. One of them is used to send messages, to encrypt messages, and one of them is used to decrypt messages. Okay? And the one used to encrypt messages doesn't have to be kept secret. So here's how it works. So Alice will create this public key, private key pair. So they have to be matched correctly. And she'll keep the private key to herself. But then she'll send out the public key to all sorts of people, to Bob, to Charlie, and maybe even Eve will get a handle on this public key. She'll get a copy of it. Okay? And then later on, Bob or Charlie or somebody wants to send a message to Alice, an encrypted message. So what he'll do is he'll take his public key and apply it to the message. And that will allow him to encrypt it. So now it's encrypted. And to read the public message, to read the encrypted message, Alice needs the private key, the one that she didn't send out, the one that she kept for herself. And so by applying that to the message, she can unlock it and see what message Charlie sent her. But on the other hand, Eve can be listening in. Again, she could make a copy of this encrypted message, see the ciphertext, but the ciphertext doesn't tell her anything. And since she doesn't have this private key that Alice kept to herself, she can't read the message. It's still secret. Okay? And you can see that this has a lot of advantages over the one-time pad, for instance, because in order to do this, Alice only needs to send this public key anything. She can print it in the newspaper. Okay? She can put it on a web page. All sorts of things. Whereas before, remember, we had to have the couriers with the handcuffed briefcases. So this is a lot easier to distribute this public key to everybody. But it does have a countering disadvantage. So the private key cryptography tends to be more secure than the public key cryptography in the following sense. The one-time pad, in fact, was completely secure. But for this public key cryptography, usually there's some assumption that Eve can't do something. In this case, that she has limited computational power. So in particular, in the case of RSA public key encryption, the public key is a pair, as I said, of very big numbers. So we'll call those N and E. So by very big, I mean, say, 300 digits long. Okay? Really, really big numbers. You don't want to have to count that high. To encrypt a message, if Bob wants to send a message to Alice, he has this public key N and E. So what he does is he takes his message and he breaks it up into blocks. Okay? And each of those blocks he's going to convert into a number that's less than N. Okay, so that kind of sets the size of the blocks he can use. And computers do this all the time. That's not really very complicated. And what he does is he takes each of these numbers and raises it to the power E. Okay, so if E is 3, he takes the cube of this number. And then he divides by n and takes the remainder. So this is called modular arithmetic, dividing by n and taking the remainder. Probably the most familiar example of modular arithmetic is if you look at a clock. Right? It goes 1 to 12, and then it starts over again. So right now it's, I don't know, about 7:20. 6 hours from now, that'll be 1:20. So that's an example of mod 12 arithmetic. So anyway, we're doing that with these very, very big numbers. And it turns out that it's really pretty hard, if all you know is N and E, to figure out what number you started with at the beginning here. Okay? But to decrypt, Alice has another number, D. And the relationship between D and E is derived from knowing the prime factors of n. So n is going to be a product of two large primes. Remember, prime has basically nothing else that divides into it except one and the number, the prime itself. And so if n is a product of two very large primes, each, I guess, about 150 digits long, then, and you know those two prime factors, then it's possible to figure out from E what D should be, or vice versa. Okay? So to create this private key, public key pair, Alice will take two large primes and multiply them together to get this big number n. But to go backwards, that turns out to be very hard. I'll get to that in a second. So anyway, to decrypt, Alice has this private key D, and she raises the encrypted message to the power D. And remember, since we've divided by n and taken the remainder, there's only so many numbers that we can work with, right? N of them. And when we do that, we'll eventually get back to the original message. And it turns out that that's the relationship between E and D that we want. That when you raise a number to the power E and then raise it again to the power D, you always get back to where you started. And so that's how she can decrypt, right? She takes this number that's already been raised to the power E and raises it to the power D and gets back the original thing that Bob sent. So the actual version of RSA that's used is a little more complicated than this, but this gets you the main idea. So as I said, to find the relationship between D and E, you have to know what the prime factors of n are. And this is a very, very hard problem. RSA is widely used. It's used, for instance, if you go onto a website like Amazon, you want to send your credit card. RSA is used to encrypt it so that no one can read that credit card number in transit. And it's believed that to break RSA, you really do have to factor n, or something equivalently hard. So anyway, looking at this poster, figuring that it was RSA, I figured I was not going to be able to break it, at least not with pencil and paper. So I turned my attention back to the computer. So I fiddled around on this computer looking to see if it had any games on it. It didn't. But it did have some programs in one directory, and it seemed a little strange. One of them was called shor.exe, S-H-O-R. And there's another kind of strange thing about this computer. It was connected to some funny black box. It wasn't really obvious what this black box was supposed to do. But putting those two features together, I became a little suspicious and wondered if somehow this black box could be a quantum computer, and the shor.exe could be running a program called Shor's algorithm. So what is that? Well, first of all, what's a quantum computer? Well, a quantum computer is a computer that uses quantum bits instead of regular bits. OK, what's a quantum bit? Well, a quantum bit, well, OK, so first of all, what's a classical bit? Classical bit has two values, right, 0 or 1. And the regular computers that we're used to store all the things in their memory in some sequence of zeros and ones. OK, so I'm going to represent these by a bit by pair of boxes. And actually, a quantum bit is also going to be represented by a pair of boxes like this. And I'll put the zeros on the left and the ones on the right. So a bit is either 0 or 1, but a quantum bit can in some sense be both at once. It's called a superposition. So here's a superposition that has kind of a big 0 and a smaller 1. So it's mostly 0, but a little bit 1. And so that wasn't supposed to be a joke. OK, so anyway, so you take this superposition that's partly 0 and partly 1. And when you measure it, unfortunately, you get one of them at random. So in this case, 2/3 chance of getting 0, and you have a 1/3 chance of getting 1. OK? And these can be any relative size. But of course, the total probability of something happening when you measure has to be 1. OK? So we can have all kinds of superpositions. And a quantum computer, as I said, is a computer made out of these things. So you can have long strings of bits, and you can have superpositions of all sorts of different combinations. So in order to get these quantum bits, or qubits as they're called for short, you need to have very, very small objects, because quantum bits have to use quantum mechanics. And quantum mechanics doesn't really operate on the scale of things that we're used to, of a person or a chair or a car. Instead, it operates at very, very small levels, like single atoms. But there are lots of people trying to figure out how to build these quantum computers. And in fact, a lot of them have been built. So here's a picture of a 2-qubit quantum computer using superconductors built in the UC Santa Barbara. So the scale of this thing is about a millimeter on a side, a little bit longer. So you can see it's already pretty small. And actually, superconductors, as these things go, are rather large for quantum computers, because superconductors have lots of special quantum properties. But of course, since it's a superconductor, you need some big tank of liquid helium in order to cool it to low enough temperatures so that it'll work. So anyway, quantum computers use these qubits. And since they can be in superpositions, they can do, in some sense, lots and lots of different calculations at once. OK, so you can see that would offer lots of extra computational power. However, there's a catch, which is, as I said, if you measure a qubit, you only get one of the two values at random. So that seems like it'd be kind of pointless, because well, you do lots of computations at once, but then one of them, you really only do one of them at random. But you'll see in a moment that there's a little more to that. And so the upshot is that for some problems that you want to solve, quantum computers are vastly more powerful than any classical computer that has been built or probably will ever be built. I mean, this is assuming we can build a large enough quantum computer to take advantage of this. But for other problems, it might not offer any advantage at all. OK, and so a classical computer is just as good. Maybe even better if the quantum computer is particularly slow. OK, so how do we manipulate these qubits? Well, I don't want to get into the physics of how we do this, but let's just talk about the mathematics. So, well, how do we manipulate bits? Well, for one thing, you can change them from one value to another. So for instance, you can take a single bit and flip it. 0 would become 1, 1 would become 0. For qubits, you have to also be able to create these superpositions. Otherwise, really nothing interesting is going to happen. So for instance, you could take 0 and turn it into a superposition, 0 and 1. So half the time, if you measure this, half the time you'll get 0 and half the time you'll get 1. But what happens if you try this same operation on a 1, a qubit that starts as a 1? Well, you also get half the time 0 and half the time 1, but there's a difference. And I've tried to represent this difference by having an upside down 1 instead of a right side up 1. And well, one reason there has to be a difference is that quantum mechanics is reversible, so that when 0 and 1, they're separate states. You can certainly distinguish them. And so these two things that you get on the right here, they also have to be separate states, also distinguishable. And the way I'm distinguishing them in this picture is to have right side up versus upside down. So the mathematics of this has a plus sign and a minus sign. OK, so more complicated operations. So if we have, say, in this example, 3 qubits, we could have a superposition of 8 possible numbers. 3 bits can go anything, can write any number 0 up to 7. So for instance, in this case, we have superposition, well, some 0, 0, 0, and some 0, 1, 0. We don't have any 0, 0, 1, but we have a little bit of 1, 0, 1, and a lot of 1, 1, 0. OK? And then we might want to do some operation on these things. So for instance, we could flip the 3rd bit, but only if the first 2 bits are both 1. OK, so that's certainly a valid thing you could do. And if you're doing this on a classical bit string, your classical computer could do that just fine. Quantum computer works the same way. So you'll see what happens is 0, 0, 0. First 2 bits are not both 1, so it stays the same. Similarly for 0, 1, 0 and 1, 0, 1. But 1, 1, 0, that gets flipped. The 3rd bit gets flipped, so it becomes 1, 1, 1. And if we had 1, 1, 1 in the original superposition, we'd get 1, 1, 0. So you see the amounts of each of these get switched. OK? And any classical computation, assuming it's reversible, a technical caveat, basically any classical computation you can convert into such a thing that will also work on superpositions. And so if you have a quantum computer, you can do any kind of computation that you can do on a classical computer. But you can also do something more. Remember on the last slide, I was able to create these superpositions. OK? So what happens if I take this state that's already in a superposition and do this same thing? So this operation, by the way, down here is called the Hadamard transform. So what happens if I do the Hadamard transform on a state that's already a superposition? That's half 0 and half 1. Well, what happens is the 0 and the 1, they each separately go into superpositions. OK, so the 0 becomes 0, 1, as before. The 1 becomes 0 and the upside down 1, also as before. OK, but then we have to somehow combine these to figure out what the real answer is, because the original was partly 0, partly 1. So what happens is these two zeros, they kind of smush together and make a big 0. And the 1s, well, something more interesting happens there. So the 1, we have a right side up 1 and an upside down 1. So those two switch together, and they cancel each other out. OK, so in this case, on the right, we have all 0 and no 1. Now, it could also be that if we had a combination where the 1 on the top was much bigger than the upside down 1 on the bottom, they wouldn't exactly cancel out. But let's just take this extreme case. So the combination of these two things is called interference. So where the two zeros going together get a bigger 0, that's constructive interference because they're working together, the zeros. Whereas the 1s cancel each other out. That's called destructive interference. So the combination of this kind of interference with regular classical computations allows you to do interesting things with quantum computers and to solve some problems that you couldn't solve with a regular classical computer in any reasonable amount of time. OK, so as I said, I looked at this box and said, well, maybe it's running Shor's algorithm. So I tried it out. Because Shor's algorithm is an algorithm that can only be run on a quantum computer. And it can only be run on a quantum computer because it uses exactly this kind of interference. And here's, roughly speaking, how it works. So remember, in RSA, we take a number and we raise it to some power, right? And eventually, if we do that, we have to get back to where we started, because there's only so many numbers less than n. We're working modulo n. And so what Shor's algorithm is an algorithm that figures out how long it takes you to get back to where you started. And using that, you can factor these big numbers like n, this 300-digit number. So roughly speaking, the way it works is, so as I said, if you raise something to the power again and again and again, eventually you get back to where you started. So the quantum computer, in order to figure out what that period is going to create a superposition over each time you get back to where you started. Okay? And so if you were to draw a picture of it, you'd say, well, OK, we'll raise, 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 and eventually we're back to where we started. Here's a spike. And we'll do it again, and here's another spike. OK, and here again, another spike. OK, and if we started with a different number, well, maybe we'd start here, OK, and then go for a while, and this would be the same distance. We'd get back to this different number, and so on. So all of this picture would be shifted over by some constant amount. OK, but the distance between the spikes would still be the same. And since we don't know where it started, we don't know how much it shifted, we can't just measure it and see where one of the spikes is. That's not going to tell us anything. But what we can do is do some constructive interference between the different spikes in the superposition. And that's done using something called the Fourier transform. So you may not think you know what the Fourier transform is, but actually you do. And probably you've just done it by looking at this picture. The Fourier transform will take some complicated pattern, and it'll tell you what the periods are in there, how often things repeat. So if you look at this picture, you'll see that there are periods. Well, there's this period, right, the distance between spikes. And there's also a double period, right, the distance between two spikes, things like that. In fact, you do it when you listen to music as well. Sound is an oscillation of the air around you. When you listen to me, for instance, the words come out of my mouth to go into the microphone. The microphone vibrates the air, right? And so you have high pressure and low pressure things. They oscillate back and forth. And if you listen to a pure musical tone, that's a particular frequency of sound. So when your brain hears the sound, it breaks it down into the frequencies. And that's the Fourier transform. So the quantum computer is doing the same thing, but it's doing it on a superposition. Okay? And then once it knows what this period is, there is some number theory that goes in that tells you how to figure out how to factor a large number. And that tells you how to break RSA. So that's what I did. I ran this program on the computer, and sure enough, it told me the periods of numbers, which allowed me to factor n. Actually, the factoring part was built in, because that's the main thing, probably, that people would want to do with Shor's algorithm, is to break codes. So it factors n, and using that, it can deduce this decryption key D, given the public key that was on this poster. And based on that, I could decode the message that the poster was saying. Here's what it was. Someone must have been telling lies about Joseph K. For without having done anything wrong, he was arrested one fine morning. As you can imagine, this did not reassure me very much. So when Alice came back, I was a little more aggressive and tried to get at her to tell me what was going on. But she demurred again. She said, I'm sorry, we're still not ready for you. I said, well, OK, but you've kept me here. Can I leave? Can you at least fix the computer? It crashes when I try to send an email. She says, OK, calm down. I'm sure it won't be much longer. We'll fix the computer. I'll send some people in right away. So she left. Indeed, some people came in, took down the poster for some reason, fiddled with the computer a bit, plugged in some extra cables. I couldn't see what that was going to do, but what could I do? So they left, and again, I tried to send an email. Same thing, it crashed. So I was kind of stuck without much left to do. So I poked around on the computer some more. And I noticed that there was some interesting message traffic coming in over these cables and leaving again. Some of it was just kind of strings of random bits, didn't seem to make much sense. Some of it, well, it took me a little while to figure out what was going on. It seemed like it was just single particles of light that my computer was registering going through this computer, and then just popping back out over one of the cables that they had plugged in. So it seems a little puzzling, but thinking again, well, the first two posters that they put up were both codes, so maybe this is a code of another kind. In fact, this might be an example of quantum key distribution. So what's that? Well, while quantum computers can be used to break codes, break RSA, quantum key distribution is a way of making codes. In particular, it's a way that Alice and Bob can establish the shared secret key. A classical key is a string of random bits that's going to be secret from the eavesdropper Eve. And then they can use this secret key to do whatever they want. For instance, they can use it with the one-time pad and have a completely secure message. So here's how it works. So Alice is going to send single photons to Bob. A photon is a quantum particle of light, the smallest possible unit of light. And she sends single photons to Bob, and there's one of 4 quantum states. So by the way, when I say a quantum state, I don't mean state like California. I mean state like state of confusion, which I hope is not afflicting too many people right now. So we have 4 possible quantum states. So we have, well, we have 0 and 1. There's lots and lots of possible quantum states, but Alice is only going to send one of these 4. So we have 0 and 1. We'll call these 2 the Z states. And then we have 2 X states. So one of them is this 0 plus 1 state with the right side up 1. And one of them is 0 minus 1 state with the upside down 1. OK? So these come in pairs. Well, they come in two types of pairs. So one is the 0, 1 pairs, the Z's. One is the superposition pairs, the X's. But if Alice wants to send a 0, she'll pick one of these 2 states. And if she wants to send a 1, she'll pick one of these 2 states. OK? And then Bob, at the other end, has to try to figure out which one she sent. So how does he do that? Well, he can measure it. So if it was one of the Z states, and he just measures it right away, well, then he'll get the same thing as Alice, right? If we had this, and he measures, he'll get 0. If he has this, and he measures, he'll get 100% 1, because it's not a superposition. On the other hand, if he does the wrong thing, if Alice sent one of the X states, and he measures right away, then he'll just get a random bit, right? So if he has this one, remember, it's equal size 0 and 1, so there's a 50% chance he'll get a 0 when he measures it, and a 50% chance he'll get a 1 when he measures it. But he has another choice. He can also do the Hadamard transform. Remember, that takes, well, it takes the 0 and the 1 states into these superpositions, but it also takes the superpositions back into 0 and 1. So I showed you how the right side up example, where the 0 and 1 went back to a 0 under the Hadamard transform. Turns out that if you have the 0 and the upside down 1, the superposition, that goes into a 1. So if Bob does this Hadamard transform, and then he measures, he'll find out which of these 2 X states he has. Okay? So he has 2 choices. He can make the Z measurement, measure it right away, or he can make the X measurement, do the Hadamard transform, and then measure it. And that will tell him, if he guesses the right one, which of these 4 states that Alice sent. If he guesses the wrong one, though, again, he'll get something random. Okay? But that's actually a good thing in this case. OK, so I'll get to that in a second. So to avoid this problem, I mean, Alice and Bob want to agree on a key. So if half the time Bob is getting a random bit, that's not going to tell him anything. So what's going to happen is after he measures it, he'll compare with Alice. And they'll say if they both sent Z, if Alice sent a Z and Bob measured Z, then they'll use that bit. If Alice sent Z and Bob measured X, or Alice sent X and Bob measured Z, then they'll throw it away. And again, if Alice sent X, Bob measured X, they'll keep it. So half the time Bob is going to guess right, and they'll keep the bit. Half the time Bob guesses the wrong measurement to make, and they'll throw it away. And so in that case, they should always get the same answer, except that there's an eavesdropper in the way. So here's where the randomness is going to play to our advantage. So Eve, in between, is going to take this quantum state and maybe do a measurement of her own. Okay? But if she guesses wrong, again, she'll get a random answer. And then she won't know what to send on to Bob. So for instance, if suppose Alice sent the 0 state in the Z, one of the Z states, and Eve makes an X measurement, and she gets one of the random results. So suppose it's this one, 0 and 1. Okay? And then she sends it on to Bob, and Bob happens to make the Z measurement also, which would match Alice's Z state that she was sent. So this is a bit that Alice and Bob are going to keep. But the problem is that Eve is sent on the wrong state. She's sent on the superposition state. And so when Bob measures it, half the time we'll get 0, which is right, and half the time we'll get 1, which is wrong. So Eve, by making the wrong measurement in here, has introduced some errors into the bits that Alice is sending to Bob. Okay? So by trying to figure out herself what the states are, what the key is going to be, she's revealing her presence by adding errors to the states. So that's what quantum key distribution does. It detects the presence of an eavesdropper. Of course, Eve has another choice. She might not make measurements, or might make only very few. But in that case, she doesn't learn anything, or very much. Okay? So in order to figure out that Eve is there, Alice and Bob will reveal a few of their bits and compare. Obviously, they can't then use those bits for keys, but Eve didn't know ahead of time which ones they were going to compare. So if she introduces a lot of errors, there's a good chance she'll get caught along the way. So putting all this together, here's the full protocol for quantum key distribution, often called QKD for short. So Alice will make up a long sequence of bits and choice of states to send, X or Z. And she'll send the corresponding sequence of photons to Bob. each photon being a qubit. So Bob will receive them, and he'll make some measurement. And then Alice and Bob will compare. Did they send this? Did Bob measure the same thing that Alice sent, or different? If it's the same, they'll keep it. If it's different, they'll throw it away. And then they have to try to figure out whether Eve has been interfering with them. So they'll choose some random subset of these bits to announce and compare. And this test subset will determine what the error rate is in the communications channel from Alice to Bob. And if the error rate is very high, then they'll conclude there's an eavesdropper listening to them, and they should throw it away. If the error rate is low, it doesn't have to be 0. I mean, after all, in a real channel, there's going to be some noise, right? It's not going to come out exactly right ever. But if the error rate is low, it could be due to an eavesdropper, but it might not be. So they'll keep that. And then they'll have to do some processing to make sure it's really secure. So first of all, since there's some error rate, they have to get rid of that using an error-correcting code. Otherwise, they'll have different bit strings, and they won't have the same shared key. And then they do something called privacy amplification. So basically, this is a way of mixing up the bits. Remember, Eve might have decided to only measure a few bits. So she might get lucky and not get caught that way. And besides, Alice and Bob were allowing a small error rate. So she could even measure a few and get partly caught. And they wouldn't really know whether it was her or just the regular errors in the channel. So anyway, they do privacy amplification, mix things up, throw away a few more bits. And that gets rid of the remaining information Eve has. So the result is you can mathematically prove that if Alice and Bob do this protocol, then Eve either has a choice. She can either reveal her presence by eavesdropping a lot, or she can eavesdrop only a little, or not at all, and then she'll end up with essentially no information about the secret key that Alice and Bob are sharing. And once they have the secret key, they can use it to send a secret message using the one-time pad. And as long as quantum mechanics is right, which as far as we know it is, there's nothing that Eve can do to find out what that message is. OK, so anyway, so as I said, I figured out or decided that they were probably using the cables in this computer to send these secret messages using QKD. So obviously, mathematically proven, nothing I can do about this. Except that looking at the traffic a little more closely, I realized they weren't using it quite right. And the way they were using it was vulnerable to an attack called the man-in-the-middle attack. So in the man-in-the-middle attack, Eve masquerades as Alice and Bob in different places. So in particular, here, I'm playing the role of Eve. Alice sends her qubits to, well, she thinks she's sending them to Bob, but actually, Eve has gotten in the way, and she's sending them to Eve instead. So Eve is intercepting these qubits. And then Alice and Eve will go through this whole QKD protocol, just like nothing is wrong. Okay? So Alice doesn't know she's only talking to Eve, so she says, well, I sent the states X, Z, 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 et cetera. And Eve answers back, doing just what Bob would do. She said, well, I measured Z, 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 X, et cetera. So they compare these, they look, say, well, the first one is different, we'll throw that away, the second one, we'll keep that, et cetera. And they talk back and forth, do the rest of the protocol. And at the end, Alice is happy. She's established a secret key she thinks with Bob, but actually with Eve. And so when she sends her encrypted message using the one-time pad, Eve at the other end can read it. Okay? Meanwhile, Eve is also talking to Bob and doing the same thing. Okay? Eve sends a bunch of quantum bits to Bob. Eve is now masquerading as Alice. So Eve sends a bunch of quantum bits to Bob, and Bob says, I've got them. You know, I measured Z, X, Z, X, et cetera. And Eve says, oh, well, I sent X, X, Z, Z, et cetera. And Eve is doing the protocol correctly as Alice would do. But you'll notice she's using different things, right? She sent different states than Alice sent, because she's doing this at the same time. But Bob has no way of knowing that Eve has gotten in between them and is masquerading as Alice. They go through the whole protocol. Bob is perfectly happy. He thinks he's established a secret key with Eve, with Alice, but actually he's established one with Eve. So Eve, remember, takes the encrypted message sent by Alice using the one-time pad, and he decrypts it. Sorry, she decrypts it using the key that she shares with Alice, and then re-encrypts it using the key that she shared with Bob. So that's what I did here. I took the messages that were coming in from Alice. I established the secret key with her, read the messages, re-encrypted them, and sent them on to Bob. Both Alice and Bob are happy. They think they're talking to each other. But actually, in between, I figured out what was going on and read their messages. And here's what I saw. So you can imagine I was a little upset by this. I thought they were doing something important, and they were just playing a game. There is a way, of course. I said you can mathematically prove that quantum key distribution is secure. Well, how do you do that? The answer is you modify the thing I said by adding what's called authentication. So when Alice authenticates her message, then Bob knows that the messages he's getting really did come from Alice and not from Eve. Okay? And similarly, Bob authenticates his messages back to Alice, so Alice knows they're really coming from Bob and not from Eve. And that way, both of them are sure that they're talking to each other and not to some man in the middle. And to do this, you need some additional private key. So actually, quantum key distribution doesn't create key from nothing. What it does is, if you start with a little bit of private key that you're using for authentication, it creates much, much more. Okay? So that's OK, because Alice and Bob then can initially set up this private key, and then they can talk as many times as they like. Whenever they're starting to use up their key, they can generate some more using quantum key distribution. And quantum key distribution, quantum computers are kind of hard to build. There was this black box that seemed to be acting as a quantum computer, but out here in the public world, the biggest quantum computers are only 12 qubits or so in size. But quantum key distribution actually has been done experimentally by many, many groups, and there are even commercial quantum key distribution devices that you can buy, at least if you have $100,000 or so lying around. OK. So back to the anecdote. So anyway, so next time Alice came in, I was, again, rather aggressive. But she said, don't worry, we're ready for you to leave. Leave? What do you mean? You kept me here all this time. She said, I'm sorry, it turns out we can't use you at all. We don't need you today, really at all. So you're welcome to leave. OK, so I wasn't really enthusiastic about this. I wanted to at least find out what it was about. But I figured, might as well leave while I can. So I did. But before I left, well, first of all, I slipped this little quantum computer into my pocket. And second, Alice handed me looked like some sort of crystal. When I got home, I examined it and saw that it had some rather intricate structure in the middle. And Alice had indicated before I left that she might be in touch at some future time. So anyway, it was a little puzzling. Alice had given me this thing. But I thought that maybe, since she said she was going to be in touch, that this was some way that she was going to use to identify herself. Because I didn't really know who it was that I'd been talking to. Alice, even if it was her real name, is not her full name, right? Not uniquely identifying her. So what's possible is that what Alice was doing was this. She was hiding some information in this crystal, which might be contain some quantum bits embedded in it somewhere. And later, she'd reveal those bits to prove that she was really who she said she was, the person I talked to before. So how does that work? Well, remember, quantum states can be in these superposition states, right? Can be 0, they can be all 0, they can be all 1. They can be half 0 and half 1 in two different ways. They can also be a different balance, right? They could be mostly 0 and a little bit 1, or the other way around, a little bit 0 and, in this case, an upside down 1. And if you don't know which of these 6 states you have in the qubit, it's impossible to really figure out, at least with 100% accuracy, which one it was. But on the other hand, if somebody tells you, well, I have this state, that's something that's relatively easy to check. Because you can make this measurement, OK? And that will tell you whether it's this state or this state. If you get this state, well, then the claim has turned out to be right. If you get this state, then it's wrong. OK? So if you do this a bunch of times, and somebody's always right, then probably they know what they're talking about. Because if they guessed wrong, if they thought it was one of these 4 states, and it was actually this one, then a lot of time it would turn up this. OK? So by doing this measurement, you can check with pretty high accuracy whether someone is telling the truth when they say they know what this qubit is. For 1 qubit, not so good accuracy. But when you do it lots and lots of times, then you can be pretty sure. So maybe I thought Alice has embedded some quantum bits into this crystal and can use them to identify who she is. And when I got home, talked to some of the other people who were also working on quantum computing, it turned out a few of them had also had kind of similar experiences to me. So a natural question we wanted to ask ourselves is, did we actually talk to the same person, or maybe there are two groups doing this type of thing? So how are we going to figure that out? Well, we have these crystals, remember, that are supposed to identify Alice. So maybe we can compare them to figure out if they're really the same, right? Because if only Alice knows what these qubits are that are embedded in this crystal, well, if they're created by different people, then they'll be different qubits. So how do we tell if they're the same or different when we don't actually know what they are? Turns out we can do that too. And the way that works is to line them up next to each other and swap them, right? So if you have a case like this, where you have two qubits that are the same state, and you swap them, then nothing changes. On the other hand, if you have qubits that are different states, like these two, and you swap them, well, then it's different. Okay? And so by doing this swap, you take these two qubits and you swap them. You look to see if anything changes or not. If it does change, well, you know they were different states. If it doesn't, well, you think they might have been the same. Okay? There's kind of a catch here in that, well, even these two states, these are pretty different states, but they still both have some zero in them, right? So they're not completely different. So when you change them and then you do a measurement, there's some probability, quantum mechanics having all this randomness involved in measurement, there's some probability that you'll think that they were the same even though they have changed in some way. But if they're really the same, then you'll always find they're the same. And there's some additional quantum wizardry involved in exactly how you do this thing, but let's not worry about that. The upshot is that there's some test you can do that if these two qubits are the same, you'll find that they're the same. And if they're different, well, at least sometimes you'll find that they're different. If you do this many times, you can have, again, high confidence that they're really the same or really different. So that's what I did. I compared with my colleagues, and we found that they were the same. So we concluded that we must have talked to the same person. So anyway, sometime later, Alice did, in fact, communicate with me and sent me a message with some instructions as to how to see that this message came from her. And more than that, it actually was that the specific message was one that she sent, that it hadn't been tampered with at all. So how does that work? Well, if Alice wants to sign a single bit message, 0 or 1, she'll take these quantum states that she's given to me. These quantum states are examples of public keys. A little more complicated than the public keys used in RSA, but nevertheless, they work kind of the same way. She'll take these public keys, and there's a big set of them, a whole long list of them. And she'll say, well, these ones on the right, they're used for 0. These ones on the left, they're used for 1. So I want to announce that if I want to send the message 0, I'm going to announce the identity of all these qubits on the left. Well, it's my left, your right. And if I want to send a 1, I'll announce the identity of all these qubits on the right. Okay? Now, only Alice knows what all of these qubits are. So if you get an announcement of this and you test them and they're all right, well, then you can be pretty sure that that came from Alice, because only Alice knows how to do that. And you see, if somebody along the way wants to pretend to be Alice and sign a message 1, well, that person needs to know what these qubits are. But Alice signed the message 0, so she only revealed what these are. So this person doesn't have the information they need to pretend to be Alice and send the message 1. Okay? And if she wants to send a longer message, well, she does this again with another set of qubits. So this is an example of something called a quantum signature. So anyway, so I got this message from Alice, read it, and here's what it said. Well, here's at least part of it. Your mission, should you choose to accept it? And the mission, if I told you, you would not believe me. Well, maybe you would believe me, given everything that's happened in the last few years, but I certainly wouldn't want to make such an accusation without any proof. I mean, I really don't have any proof, right? For all you know, I'm making all of this up. But hold on, wait a second. Maybe I can't prove it to you, but remember there's these other colleagues that had the same experience. And they also got these qubits from Alice. So maybe I could prove it to them. Because after all, this is an example of something called a digital signature. So what's a digital signature? So digital signature is, again, a public key cryptographic thing. And in fact, you can do this using classical public key cryptography, for instance, using RSA, with things turned around. So again, you have a private key, public key pair. Public key is given out to a lot of people. But now things are reversed, because now you use the private key to send the message, to sign it, and the public key to verify it, to receive the message. Okay? So Alice wants to sign a message, and she wants to send it to Bob, and Bob wants to be sure the message really came from Alice. So Alice is going to take her private key, use that to sign the message, and Bob then uses his public key to verify it. Now Bob, if he wants, can send this message on to somebody else, to Charlie. Charlie also has the public key, and both of them put these two things together, the public key and the signed message, together in the same way. So if Bob concludes that the message really came from Alice, Charlie will also conclude that. Okay? So these are kind of the two components of the signature. So Alice knows that Bob can't change the message, because Bob has the public key, which is used to verify the message, but not the private key, which is used to sign it. So it's important to note this is one way in which a digital signature is different from a regular handwritten signature. The signature is attached to the message. A handwritten signature, you could copy it, lift it up, and put it identically on a different contract, and there'd be no way of telling that, a different message. Whereas with a digital signature, you can't do that. It's a unique thing that's associated with a specific message. And that's important, right? Because otherwise, you might want to change a contract that says, I will pay you $1,000 to a contract that says, I will pay you $1 million, right? And that clearly would not be secure. So anyway, so that's what Alice wants to know. Alice wants to know that Bob can't change the message, even though he has the public key that allows him to verify it. Bob wants to know that he can take this signed message and, if necessary, prove in court that Alice really signed it. Okay? So what he wants to know is that Alice can't disavow this message, that when he passes this message on to Charlie, Charlie will agree with him that it was really signed by Alice. Okay? So classically, this is why public key cryptography is good, because Bob and Charlie both need a copy of this public key. Okay? And nevertheless, they can't fool each other. Whereas if they had a private key cryptography, they'd be kind of on the same basis as Alice, and either of them would be able to sign messages too. But there is one important thing here, is that Bob and Charlie have the same public key. So anyway, so again, maybe getting back to the anecdote, maybe I can prove that this mission really was offered to me by Alice, to my colleagues, who also have these quantum states in the crystals, same public key as me. Remember, we did this swap test to see that they're the same. But it turns out that these quantum public keys are not quite the same as classical public keys. Classical public keys, you can look at them and see that they're really the same. Quantum public keys, we're doing this swap test, which is not quite as good. And the reason it's not as good is that there's some quantum trickery that Alice could use to get around this. So Alice, instead of just sending one copy of the public key to me and one copy of the public key to my colleague, say Bob and Charlie, she can do what's called an entangled quantum state, which is a superposition of two different things. In one of them, Bob has one value of the public key, and Charlie has a different value. And the other thing, they're reversed. Charlie has the first value, and Bob has the second one. Okay? So one of them, Bob has first, Charlie has second. The other one, they're switched. And that means that if Alice sends the message saying, well, here's the value of this public key, then whenever Bob says, yes, that's right, I measured and that's what it really was, Charlie will say, no, 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 it's something different. Okay? But at the same time, because it's a superposition of these things with the two keys swapped, it still passes the swap test. Right? What happens when you swap these two things? Well, the first thing in the superposition becomes the second thing. And the second thing becomes the first thing. But they're both present in the superposition. So this is a state, this entangled state, where the public keys for Bob and for Charlie are different, but the state doesn't change when you switch them. Okay? That's kind of weird. It can't happen classically, but quantum mechanically it can. And so that's what Alice did. She fooled us by sending out things that we thought were the same public key, but were different. So when I measured this message and concluded that it really had come from Alice, I showed it to my colleagues, and they said, no, 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 you're making it up. That's why I have no proof. Okay, so but you can modify this procedure to really make a secure digital signature, or using quantum states as public keys. And the key to that is to repeat, to do this very many times for the same message. And the reason that helps is, well, when we have the superposition, remember, you measure it and it's random, right? We had the superposition, Bob has one value, Charlie has a different one with the reverse. And Alice has no way of controlling, when Bob measures, which of these two things he'll get, whether he'll get the first key or the second key. So she has no way of knowing ahead of time whether Bob will accept the message or Charlie will accept the message. So if you do this many times with many different keys, statistically, half the time Bob will accept and half the time Charlie will accept it. And so they'll each accept roughly the same number of times when you repeat this many times. And statistically, it all averages out. So they'll reach the same conclusion most of the time. And so using that, you can make a secure quantum signature using secure digital signature using quantum states. It's unfortunately very inefficient, so it's probably not something that one would really want to use in practice. But it has advantages over classical methods of digital signatures, which again rely on some computational hard problem, like factoring for RSA. And if computers improve, better algorithms, quantum computers are built, then RSA would become insecure, and we'd need to find another method of digital signature. OK, so that's really the end of the story. I never heard from Alice again after that. But I hope you've at least learned something about cryptography in hearing about this. So here's some high points to take away with you. So cryptography works based on a system of keys. They can either be secret keys, private keys, or public keys. But basically, there has to be some advantage that the legitimate users of this cryptographic system have over an eavesdropper. And that's embedded in the key. So you have the private key things like the one-time pad, which is completely secure. It requires a very, very long key. On the other hand, you have public key systems like RSA, which are very flexible. You don't have to be careful about where you give out the public key, but have limited security, only when some hard computational problem can't be broken. And for instance, RSA is widely used, but if you could build a quantum computer, you could break it. On the other hand, quantum computers are also good for creating codes. They can use this quantum key distribution, which you could use to establish secret keys, and then use the one-time pad all you want. Quantum states are good for other kinds of cryptography. In cryptography, actually, there's lots and lots of things you can do. Encryption, sending secret messages, is the one we normally think about. But digital signatures is also a cryptographic application. Very, very useful. And some others which are maybe not quite as useful, but definitely have applications. And nowadays, I think it may be even legally possible to have a legally binding contract that you've signed with a digital signature. And quantum states could possibly be used to make this more secure. So no one ends up very confused. Let me finish with some disclaimers. Quantum computers in the real world have been built, but nothing large enough to factor a 300-digit number. Okay? The largest quantum computers in terms of qubits is, like I said, maybe around 12 qubits today. There's lots of different ways people have tried to build quantum computers. That's a subject for another talk. I guess we've had some talks on the subject before. But QKD, on the other hand, that really is in existence today. People have done that. You can, as I said, you can buy them. And it's not clear whether anybody's about to start using them to send real secret messages that they really care about. But it's something that's certainly possible in the next few years that people will do that. So that's pretty much all I had to say. Thanks for coming.
So this is the Q&A portion of the evening. We have about 20 minutes for questions. We have two people in the aisle, one in each aisle. So if you have a question, please raise your hand. And then we'll find you with the microphone. And we'll have a question. Go ahead, sir.
I understand the American government has expressed some reticence to allow high-end cryptography into the public sphere, fearing that various groups will be able to keep their activities out of the hands of the American government. Can you update us on the status of that situation?
Yeah, so I'm not completely up to date. In the 90s, the US government did in fact try various export controls on strong cryptography. There were two problems with this. One is that whenever it came to a court test, it was ruled against them that you could export cryptography. The other problem is that people outside the US had created very secure crypto systems and distributed them freely over the net. So it was all kind of pointless, because if you wanted to, it was not at all difficult to get strong cryptography. So my understanding is that they've mostly given up on that. In the specific case of quantum cryptography, this is still kind of at an early stage. So in some sense, they haven't even attempted to crack down on it. There is, I believe, some classified research going on in quantum cryptography, but I don't really know too much about that for obvious reasons.
Okay, another question, just raise your hand wherever you are if you have a question, and we'll get a microphone to you. Any questions? It's a very cryptic audience tonight. Here's one right here.
Okay, so you made a convincing case that this is really secure, but every time something's been really secure, like RSA, you've just shown that there's a new technology that obsoletes it in a sense. Where
Right.
do you think the attack to quantum cryptography can come from?
Right. So I think this is of kind of a different nature. Well, okay. So cryptography as a field is evolving. Until roughly around World War II, it was kind of an ad hoc thing. Since World War II, cryptography played such a big role in World War II. There's been a lot of research money got into it. It's become a very mathematical field. So we have kind of a much better grasp, I think, of things being secure or insecure. But even today's crypto systems, there's this problem that we just think they're secure. The problem is that we find it very hard to prove, mathematically prove, that a problem that seems to be hard really is hard to solve, hard in a computational sense. But quantum key distribution, that's something we really can prove, assuming quantum mechanics is right. Now, I don't expect quantum mechanics to fail. It is possible there's attacks against real quantum key distribution systems. And the reason for that is that when you actually physically implement this system, it might not work exactly the way the idealized protocol that I showed you says it should work. Okay? And so that's something that really we need to get a handle on, to figure out the ways in which these realistic systems that people are building deviate from this ideal protocol, and whether that's going to impair security at all. I think it is possible to make it really secure. I'm not completely confident that the ones people are building today are really secure in that sense. But there's a pretty good chance, at least if you use them for if you don't try to push them to their limits. Let's put it that way.
Okay, question in the back corner.
Yeah, just a question. In the news recently, we've seen things like attacks on the HD DVD and Blu-ray recently. And I'm wondering if quantum cryptography has anything to offer in that range where you give people both the ciphertext and the key, and you have to obfuscate somehow the whole decryption process.
Right. So attacks on DVD encryption, really what they want to do is they want to do copy protection. They want to make it impossible that even though you have a copy of this DVD and you can watch it, they want to make it impossible for you to make a copy of that and give it to someone else. The problem is that that's impossible. Which is why these things keep getting broken. There's actually no way, I mean, by any reasonable definition of copy protection, that you can do that. And one easy way of seeing that is, well, you watch the movie, right? So you've seen it. That's the memory of it is a copy. And there's really no way around that. There might be some way that quantum cryptography techniques could help in some other arenas that are related, like copying programs. You don't see everything that the program can do, computer program can do, so maybe quantum cryptography can help in that. That's something that some people are working on, but there's not really any results, concrete results that I can point you to there. But as far as DVDs, music, things like that, you watch the whole thing. So there's really no way around it.
Okay, there's a question down here in the front corner.
So what needs to be done to the message so that the encryption key or the public key and the decryption key or the private key can be different? You know what I mean?
Yeah. So it really depends on the specific cryptographic system. So in the case of RSA, you raise things to one power to encrypt, and you raise them to a different power to decrypt. So that's why they're different keys, because you're using one power and then a different power. In the case of the one-time pad, well, you're doing one thing forward, and you're doing the same thing in reverse. So what you need is something that's easy to do one way and hard to do the other way, even when you have the key. Even when you have at least a public key that lets you do it forward. I mean, so the mathematical term for these things, the private key encryption is related to something called a one-way function, where it's easy to compute forward, so that's encryption, but it's hard to compute backwards. That's decryption, if you don't know where you're starting. Whereas the public key cryptography is related to something called a trapdoor function. So again, it's one way, easy to compute forward, hard to compute backwards, but there's this trapdoor that lets you compute it backwards. And it's not, I know, a complete answer to the question, but I don't really have a better one.
Okay, question in the corner.
Isn't all of this predicated on there being no breakthrough in mathematics that will allow factoring of very large numbers? If that breakthrough happens, will that make quantum cryptography obsolete as well?
No. So, okay, it depends on exactly which question you're asking. So obviously, if somebody comes up with a really good way to factor numbers on a classical computer, well, then we won't need a quantum computer to do that. There's other things that a quantum computer can do that would still be useful, just not necessarily related to cryptography. Although some of them are, and in fact, it's possible there's some cryptographic systems that would not be broken by factoring, but would still be broken by a quantum computer. So that's one answer. The other answer is quantum key distribution would still be useful, and in fact, would really even be more useful in that case, right? Because now RSA is no good, because anyone can break it using a regular classical computer. But now we need some other method of encryption. So people will turn to private key encryption, and maybe quantum cryptography has a place in that.
Okay, question here.
My question's not that important, but did that story actually happen to you?
Well, so the very, very beginning, where I was at a conference in Washington, D.C., that happened. The rest of it did not.
Question in the front row.
In a classical computer, a change in a bit is between a high voltage and a low voltage. But at a quantum level, a qubit, how would I determine between the states of qubits, and what is the maximum possible amount of qubits I can have?
Right. Well, so there's no intrinsic. Well, okay. Okay. So there's lots and lots of ways that people are trying to build quantum computers, and the different ways, they have different ways of encoding these qubits. So for instance, I showed you a superconducting qubit. Well, okay, maybe that's not a good example, because there's also lots of ways to build superconducting qubits. One way might be to have, so superconductors work using these things called Cooper pairs, which are pairs of electrons. And so one way of building a superconducting qubit is to have either a Cooper pair here or a Cooper pair here. So it's the position of this Cooper pair. In others, for instance, you have trapped atoms, single atoms, that are ionized. They have one electron in their outer shell. And the electron is either in a low energy state or a higher energy state. And it tends to stay there for a while. So that's another way of building a qubit. We have here in the front row, Raymond Laflamme. He has an NMR quantum computer over at the University of Waterloo. So that has nuclear spins. So you have an atom, but now it's a molecule. You have a tube full of molecules. And in each molecule, you have atoms, and the atoms have nucleus, right? Nucleus, it turns out, has this property called spin, which is a little like the spin that you think of, something turning around, but also kind of different. It's a quantum property. And so anyway, so it's spinning one way versus spinning the other way. That's the qubit. So you see there's lots of different ways of doing this. As to the number of qubits, well, it's hard to build these things. So right now we don't have very many, but the intrinsic limits of how many you could possibly have, basically there's no limit. I mean, you could have as many of them as you could have regular classical bits in a classical computer, right? And my computer is rather old, so it only has 512 megabytes. So that's like 200,000. So it's 200 trillion bits, something like that. Sorry, factor of 8, 400 trillion. Wow. You can see I'm fried here. 4 trillion bits. So that's a lot, right? And so in principle, you could build quantum computers that are just as large. In practice, that's a really hard thing to do.
Okay, and with that, I think I'd like to thank Dr. Gottesman one more time.